The universe holds a secret we are only beginning to grasp. Everything we can see when we look up at the night sky, all the stars and galaxies, might represent less than half of what is actually out there. Invisible forces, undetectable by our finest instruments, appear to be pulling and shaping the cosmos in ways we cannot yet understand. This is the mystery of phantom forces between galaxies, and it suggests we could be missing half the universe. By the end of this, you will understand the startling evidence for this hidden cosmos and what it means for our very reality. We will uncover why galaxies move in ways that defy physics and explore whether dark matter or something even stranger is at work. What does it mean for our existence if most of the universe is completely invisible to us? These phantom forces are the gravitational signatures of an invisible actor on the cosmic stage. We observe their effects clearly, a powerful and unexplained tugging between galaxies, but the source itself remains completely hidden from our view. The story of their discovery begins not with grand intergalactic motions, but by looking closely at individual galaxies themselves. Astronomers studying how stars orbit within spiral galaxies made a startling observation. According to the laws of gravity established by Isaac Newton and refined by Albert Einstein, stars on the outer edges of a galaxy should move much more slowly than those near the bright, dense center. This is simple physics, much like how the outer planets in our solar system take far longer to orbit the sun than the inner ones, but the data told a completely different and utterly baffling story. Stars racing around a galaxy's outskirts were moving just as fast as those near the core. This was impossible. The visible mass of the galaxy, all the stars and gas we could see, simply did not provide enough gravitational glue to hold these speeding outer stars in their orbits. At those velocities, the galaxies should have flown apart, scattering their stars into the void, yet they remained intact, spinning gracefully. The only logical conclusion was that there had to be far more mass than we could account for. A vast, unseen halo of something was enveloping each galaxy, providing the extra gravitational pull to keep everything together. It is the cosmic equivalent of hearing distinct, heavy footsteps in a room you know to be empty. You cannot see what is making the sound, but you are absolutely certain that something is there with you. This eerie discrepancy between what we see and what must be there is the fundamental clue that launched the greatest treasure hunt in the history of science, a search for the missing half of our universe. This cosmic detective story starts nearly a century ago with a brilliant and often contentious astronomer named Fritz Zwicky. Working at the California Institute of Technology in the 1930s, Zwicky turned his attention to the Coma Cluster, a vast gathering of thousands of galaxies millions of light-years away. He meticulously measured how these galaxies were moving relative to one another, and what he found was deeply perplexing. The individual galaxies within the cluster were hurtling about at astonishing speeds, so fast that the collective gravity of all the stars and gas visible to him could not possibly hold the cluster together. By all rights, this immense cosmic city should have disintegrated, its galactic residence flung out into the emptiness of space, yet it remained a stable, bound structure. Zwicky knew the math was unequivocal. There had to be more, much more than what met the eye. He concluded that some form of invisible matter must be present, providing the immense gravitational glue needed to keep the cluster from flying apart. He called it Dunkelmaterei, which in his native German means dark matter. It was a revolutionary, almost heretical idea for its time, and it was largely dismissed by the astronomical community. How could you propose something you could not see, It seemed like a fudge, a desperate invention to patch a hole in the equations. The concept would lie dormant for decades, a curious footnote in the annals of science, until another astronomer picked up the thread. In the 1970s, Vera Rubin, working with Kent Ford, was studying the rotation of individual spiral galaxies. Her precise measurements of star velocities provided the undeniable, concrete evidence that Zwicky's radical idea was correct. Galaxy after galaxy showed the same impossible star motions, confirming that this missing mass was not a fluke of a single galaxy cluster, but a universal phenomenon. Rubin's work transformed dark matter from a fringe hypothesis into a central problem in physics. The initial skepticism was finally overwhelmed by the sheer weight of data. This historical journey, from Zwicky's stubborn intuition to Rubin's meticulous confirmation, shows how curiosity and careful observation can reveal a universe far stranger and more wonderful than we ever imagined. It was the crucial first step, the moment we realized we were not just missing a few pieces of the puzzle. We were missing an entire box. The evidence for this hidden reality only grows stronger with every technological leap we make. Our most powerful telescopes, orbiting high above the distorting blanket of our atmosphere, peer deeper into space than ever before, and they return with data that consistently defies expectation. One of the most compelling pieces of evidence comes from a phenomenon predicted by Einstein himself, a cosmic illusion known as gravitational lensing. This occurs when the immense gravity of a massive object, like a galaxy cluster, acts like a lens in space, bending and warping the light from even more distant objects behind it. Astronomers can map this distortion, creating a precise picture of how much mass is in the foreground cluster and where it is concentrated. Time and again, these maps reveal a shocking truth. The visible galaxies in the cluster account for only a small fraction of the mass creating this gravitational lens. The majority of the mass is completely invisible, a phantom presence warping the fabric of space-time itself. It is a direct observation of the unseen. Furthermore, when we zoom out to look at the universe on its grandest scale, the evidence becomes overwhelming. The cosmos is not a random scattering of galaxies. It is a vast, intricate web with long filaments of matter connecting dense nodes and surrounding immense, empty voids. This magnificent structure, the cosmic web, could not have formed under the gentle tug of gravity from the matter we see. The visible universe simply does not have enough gravitational muscle to pull matter into such a specific and elaborate architecture. Computer simulations show that to build the universe we observe, you need 5 times more gravity, 5 times more mass than all the stars, planets, and gas combined. Even the motion of entire galaxy clusters as they drift through the cosmos points to these unseen forces. They move with a momentum that suggests they are being pulled by gravitational tides from concentrations of mass we cannot detect. These are not minor accounting errors or small quirks in the data. They are fundamental, glaring inconsistencies in our understanding of how the universe works. It is the equivalent of hearing a full symphony orchestra playing in a room you have thoroughly searched, finding only a single violin. The music is undeniable, but the musicians are utterly invisible. This forces astronomers to confront a profound and humbling question. If everything we see is just the tip of the cosmic iceberg, what breathtaking, unseen reality lies hidden beneath the surface? So the leading theory points to an invisible substance called dark matter. This is the primary suspect, the cosmic glue that provides the extra gravitational pull we so clearly observe. Unlike the atoms that make up you, me, and every star we can see, dark matter does not interact with light at all. It does not emit it, absorb it, or reflect it. It is, by its very nature, completely and utterly dark. This is why our telescopes, which are essentially sophisticated light collectors, cannot see it directly. Yet it has mass and it exerts gravity. This single property allows it to shape the entire universe from the shadows. Current models suggest a staggering distribution of cosmic stuff. All the ordinary matter we know and love, the stuff of planets and people, accounts for a mere 5% of the universe. Dark matter, this invisible scaffolding, is thought to make up about 27%. That means there is over 5 times more dark matter out there than all the regular matter combined. But what could it possibly be made of? Physicists have proposed exotic theoretical particles. One leading candidate is called a WIMP, which stands for Weakly Interacting Massive Particle. As the name implies, these particles would have mass but interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to catch. Another candidate is the Axion, a particle that would be extremely light but exist in vast numbers. The hunt for these particles is one of the most intense efforts in modern science, involving detectors buried deep underground in old mines to shield them from cosmic interference. Yet, despite decades of searching, not a single dark matter particle has been definitively confirmed. We are surrounded by an ocean of something we cannot touch, see, or directly measure, yet we see its waves crashing against the shores of every galaxy. Its gravitational fingerprints are everywhere, from the way individual galaxies spin to the grand design of the cosmic web itself. This invisible architecture might be the key to understanding everything, a hidden framework upon which the visible universe is built. But what if this elegant solution is not the entire story? But the mystery deepens because not every scientist is convinced dark matter is the only answer. Some researchers propose a far more radical idea. What if there is no missing matter at all? What if instead our understanding of gravity itself is incomplete? This idea suggests that the phantom forces we observe are not clues to an invisible substance, but proof that Isaac Newton's and Albert Einstein's laws of gravity, while perfect for our solar system, break down on the immense scales of galaxies and beyond. The most prominent of these alternative theories is known as modified Newtonian dynamics, or MOND. It proposes a simple but profound change to the equations of motion. At extremely low accelerations, like those experienced by stars on the outskirts of a galaxy, gravity would become slightly stronger than the standard laws predict. This tiny tweak could, in theory, explain why those outer stars orbit so quickly without requiring any extra invisible mass. For certain galactic rotations, MOND predictions match the observations astonishingly well. It is an elegant solution that does away with the need to invent an entirely new, undetectable form of matter. The appeal is undeniable, yet this alternative faces its own formidable challenges. The most famous evidence against it comes from a cosmic car crash known as the Bullet Cluster. This is a violent collision between two galaxy clusters. During such an event, the clouds of hot gas within the clusters slam into each other and slow down, much like two clouds of smoke merging. But the mysterious source of the gravity, as mapped by gravitational lensing, does not slow down. It plows straight through the collision, completely separate from the visible gas. For most scientists, this is the smoking gun. It shows that the mass causing the lensing is indeed a substance that interacts only through gravity, just like dark matter, and is not an inherent property of the visible material or a modification of gravity's laws. MOND, in its basic form, struggles to explain this clear separation. This ongoing debate is not a sign of failure in science. It is a sign of its vibrant health and creativity. Confronted with a universe that refuses to conform to our expectations, Physicists are exploring every possible path, from hunting for invisible particles to rewriting the fundamental laws of physics. They are even considering ideas from quantum gravity or the existence of extraspatial dimensions that could subtly alter how gravity behaves. Each idea is a door to a new reality. The truth of our cosmos may be something far stranger and more wonderful than dark matter or modified gravity alone. It might be a combination of both or something entirely outside our current imagination. This is the thrilling frontier of discovery, where our deepest mysteries push us toward our greatest revolutions in understanding. Just as we grapple with the mystery of what holds galaxies together, we find an even more powerful force working in the opposite direction. This is dark energy, the enigmatic entity that is not pulling the cosmos inward but actively pushing it apart. Its discovery in the late 1990s sent a shockwave through the world of cosmology. Two independent teams were observing distant stellar explosions, known as Type 1, a supernova, to measure how the expansion of the universe has changed over time. They expected to find that the gravitational pull of all the matter in the cosmos was gradually slowing this expansion down. Instead, they found the exact opposite. The expansion of the universe is not slowing at all. It is accelerating, getting faster and faster with every passing moment. Galaxies are flying away from each other at an ever-increasing rate, as if some repulsive force, some anti-gravity, is woven into the very fabric of space itself. This invisible driver was named dark energy, and its estimated contribution to the universe is staggering. If dark matter makes up about 27% of the cosmos, and normal matter a mere 5%, dark energy is believed to constitute the remaining 68%. It is the dominant component of everything that exists, yet its nature is arguably more perplexing than that of dark matter. One leading explanation reaches back to an idea from Albert Einstein himself, something he called the cosmological constant. This is a property of empty space itself, a constant energy density that fills the vacuum and exerts a negative pressure, driving the universe apart. Another concept ties it to the bizarre, fluctuating energy of the quantum vacuum. But these are just names for a profound ignorance. We are essentially labeling the problem rather than solving it. So here we stand, in a universe dominated by two invisible actors we do not understand. On one hand, dark matter provides the gravitational scaffolding that pulls matter together to form galaxies and clusters. On the other, dark energy provides the counterforce, pushing the cosmic architecture apart on the grandest scales. They are locked in a dynamic and eternal tension, a cosmic tug of war that will ultimately decide the fate of everything. Their interplay is the central drama of modern cosmology. To solve the puzzle of the missing universe, we cannot just look for one invisible component. We must unravel the dual mystery of both the hand that builds and the hand that tears apart. To peer directly into the universe's infancy, we must listen to its oldest echo. This echo is the cosmic microwave background radiation, a faint hiss of energy that fills every cubic inch of the cosmos. It is the cooled remnant of the Big Bang's initial flash, a baby picture of the universe when it was just 380,000 years old. At that moment, the hot, dense plasma of the early universe cooled just enough for the first atoms to form, allowing light to break free and travel across space for the first time. That ancient light has been stretched and cooled by the universe's expansion over billions of years, arriving at our telescopes today as microwave radiation. It is the most important fossil we have from the dawn of time, and it holds encoded within it the precise recipe for our entire reality. Missions like the Planck Space Observatory have mapped this radiation with breathtaking precision, creating a detailed temperature map of the entire sky. This map is not a featureless blanket. It is a tapestry of incredibly tiny variations, minute fluctuations in temperature and density that represent the seeds of all future structure. These tiny ripples are the gravitational blueprints for everything to come, the regions where matter would eventually clump together to form galaxies and the vast cosmic web. The critical question is, what do the patterns of these ripples tell us about the ingredients that created them? When cosmologists feed these precise measurements into their models of the universe's evolution, the results are unequivocal and staggering. The patterns we see only make sense if the universe contains exactly the amount of dark matter and dark energy we have inferred from other observations. The fluctuations are too pronounced, the structures too defined, to have been sculpted by the gravity of normal matter alone. This fossilized light acts as a final, irrefutable arbitrator. It confirms that the phantom forces we detect are not a modern anomaly. They were woven into the fabric of the cosmos from the very beginning. The blueprint for our invisible universe was set in stone, or rather in light, before a single star had even formed. The cosmic microwave background is our most direct line of evidence, a message from the past that validates our present conclusions about the cosmos's hidden composition. It tells us that dark matter and dark energy are not just convenient explanations for what we see today. They are fundamental, primordial components without which our universe would look completely different, a formless void without galaxies, stars, or us. This realization is both humbling and electrifying. We are decoding the universe's birth certificate, and it states clearly that most of reality is forever hidden from our view. These colossal assemblies of galaxies are the ultimate testing grounds for our theories. A single galaxy cluster can contain thousands of individual galaxies, all swimming in a superheated sea of gas that glows fiercely in X-ray light, and all bound together by the immense gravity of a hidden king, dark matter. To understand this complex crime scene, astronomers use every tool at their disposal. They point X-ray telescopes at the cluster to map the distribution of this scorching intergalactic gas, which represents the bulk of the normal, visible matter. Then they use optical telescopes to carefully measure the subtle warping of background starlight, an effect called gravitational lensing, to create a map of the cluster's total mass, both seen and unseen. What they find is always the same shocking story. The map of the total mass, the true gravitational landscape, does not match the map of the visible gas and stars. The gravity is coming from somewhere else entirely, a vast and invisible halo that holds the entire cosmic city together. The most famous example of this is the Bullet Cluster, a system born from a violent collision between two smaller clusters. This event acted like a perfect natural experiment. Think of it as two clouds of smoke slamming into each other. The clouds of hot gas from each cluster, which are made of normal matter, collided and slowed down just as you would expect. But the mysterious dark matter from each cluster, which does not interact with anything but gravity, did not slow down. It sailed right through the carnage. The result, the gravitational lensing map, shows two distinct clumps of mass that have completely separated from the visible clouds of gas they once belonged to. This is the closest thing we have to direct proof of dark matter's existence. It shows us that the source of gravity is not tied to the stars or the gas. It is a separate, shadowy substance that can be pulled apart and mapped on its own. Each cluster we study adds another piece to this puzzle, allowing us to refine our models of what dark matter might be and how it behaves. They are not just distant curiosities. They are active laboratories where the fundamental rules of the cosmos are being written, and where we are slowly, painstakingly learning to read them. To test these grand ideas, we turn to the most powerful tools of the digital age. Supercomputers allow us to build entire universes from scratch, running vast cosmic simulations that begin with the smooth soup of the Big Bang and fast forward through billions of years of evolution. These are not simple animations. They are complex mathematical models that encode the laws of physics, including our best guesses for the behavior of dark matter and dark energy. The goal is breathtakingly ambitious: to see if our theoretical ingredients can, over eons of simulated time, bake a universe that looks exactly like our own. Pioneering projects like the Millennium simulation did precisely this, creating a virtual cosmos so vast it contained billions of particles representing dark matter halos. The result was a stunningly familiar cosmic web, a digital tapestry of filaments, clusters, and voids that mirrored the large-scale structure astronomers observe with their telescopes. This virtual universe told a clear and compelling story. When the simulation runs with only the gravity from normal matter, the result is a formless, barren void. Galaxies do not form, the cosmic web never emerges, but when the invisible gravitational scaffolding of dark matter is added to the model, everything changes. Matter begins to clump in exactly the right ways, building the magnificent galactic structures we see in the real night sky. These simulations do more than just recreate what we know. They make testable predictions. They tell observers where to point their telescopes, predicting regions of space where dark matter should be most dense, guiding the hunt for its subtle effects. It is the ultimate dress rehearsal, a way to experiment with the fundamental rules of reality itself. While a simulation is not proof, it is a powerful framework that connects theory to observation. It shows us that the idea of a dark matter universe is not just consistent with the evidence. It is the only model that successfully builds the complex, beautiful cosmos we call home. Deep beneath the Earth's surface, in abandoned mines and caverns shielded from cosmic interference, scientists are laying the most delicate traps. These are the direct detection experiments, the front line in our hunt to catch a dark matter particle in the act. Their design is a masterpiece of isolation and precision. By going underground, they are protected from the constant rain of cosmic rays and other particles that would completely drown out the unimaginably faint signal they are searching for. Inside these pristine chambers, they place vats of ultra-pure liquid xenon or other exotic materials, chilled to extreme temperatures and watched over by arrays of exquisitely sensitive light sensors. The goal is to witness a single telltale event. The hope is that once in a great while, a dark matter particle from the vast halo surrounding our galaxy will, by sheer chance, bump into the nucleus of an atom in this liquid. This tiny collision would produce a minuscule flash of light and a release of charge, a signature that the detectors are built to capture. Experiments with names like LUX, Xenon, and DOMA represent decades of work and technological refinement, all focused on this one elusive moment. Yet, after years of searching, the results have been a profound and telling silence. The detectors have not found a definitive, repeatable signal, but in science, a null result is not a failure. Each experiment that comes up empty-handed is actually a tremendous success. It tells us what dark matter is not. It rules out entire families of theoretical particles, narrowing the search and forcing physicists to refine their models and look in new, more exotic places. The task is monumental, like trying to hear the faint rustle of a single leaf falling in the middle of a roaring stadium. It requires immense patience, but the potential reward is a revolution in our understanding of the physical world. The hunt continues, driven by the unwavering belief that the universe's biggest secret is ultimately within our grasp. While some search deep underground, others turn their gaze to the heavens for a different kind of evidence. This is the hunt for indirect detection, a method that seeks not the dark matter particle itself, but the fallout from its potential demise. The theory suggests that when two dark matter particles collide, they might annihilate each other in a flash of energy, transforming into secondary particles we can actually see, such as gamma rays, the most energetic form of light. Or a single dark matter particle might spontaneously decay into a shower of other known particles. Our best chance of spotting this cosmic fireworks show is to look where dark matter is thought to be most densely packed. Astronomers point powerful telescopes toward the hearts of galaxies, including our own Milky Way, and toward dwarf galaxies that are believed to be almost pure dark matter. These regions are the prime hunting grounds. Instruments like the Fermi Gamma Ray Space Telescope constantly scan the sky, building a map of the universe's most violent events. Another incredible detector, IceCube buried deep in the Antarctic ice, watches for not light but neutrinos, ghostly particles that could also be a byproduct of dark matter interactions. The data from these observatories has produced thrilling hints. Unexplained excesses of gamma rays have been detected from the galactic center, a place teeming with potential dark matter. But the universe is a messy place. These signals could also be coming from more mundane sources, like undiscovered pulsars or other high-energy astrophysical objects. The challenge is to separate a true dark matter signal from the cosmic background noise. This method turns the entire cosmos into a giant laboratory. We are not building a detector, we are using the universe itself. Every unusual spike of energy, every anomalous particle stream, is a clue in this grandest of all treasure hunts. Each one is a potential message, a signpost left by the invisible universe as it interacts with itself, and we are only just learning how to read the map. If we cannot catch dark matter in the wild, perhaps we can create it ourselves. This is the daring proposition at the heart of the world's largest machine, the Large Hadron Collider. Buried beneath the border of France and Switzerland, this 27-kilometer ring is a cathedral of human ingenuity, designed to accelerate protons to within a hair's breadth of light speed before smashing them together. The goal is to shatter the familiar components of our reality, recreating the unimaginably hot and dense conditions that existed just moments after the Big Bang. In that fleeting, energetic fireball, physicists hope to forge something entirely new, the exotic particles that make up the dark universe. The challenge is that we would not see these particles directly, even if we made them. They would slip through the massive detectors unnoticed, just as they do in deep space, but their creation would leave an undeniable calling card, a signature of missing energy. The laws of physics demand that energy be conserved. It cannot simply vanish. So if scientists meticulously account for all the energy and momentum going into a collision and find a significant amount has inexplicably disappeared, that missing energy could be the telltale sign that dark matter particles were created and then fled the scene immediately, carrying their energy away with them. It is a cosmic game of subatomic billiards where the only evidence a ball was ever there is the unexpected motion of all the others. So far, the collider has not found this definitive signal. But its experiments have been far from fruitless. They have systematically ruled out entire families of theoretical particles, narrowing the search and telling us where not to look. Each null result is a step forward, pruning the tree of possibilities and forcing us to refine our theories. This monumental effort represents a profound synthesis of the incredibly large and the unimaginably small. It connects the vast, galactic-scale evidence for dark matter with the microscopic quest to understand its fundamental nature. We are using the most advanced tools of particle physics to answer the grandest questions of cosmology, attempting to summon the invisible architect of our universe into being, if only for a fraction of a second. This universal anomaly is written in the very motion of the stars themselves. To understand it, astronomers create what is known as a rotation curve. It is a simple graph that plots the orbital speed of stars against their distance from the center of their galaxy. The prediction from Newtonian physics is beautifully straightforward. Just as the outer planets in our solar system orbit the Sun more slowly than the inner ones, stars on the outskirts of a galaxy should be moving at a far more leisurely pace than those caught in the dense, bright traffic of the core. The gravitational pull weakens with distance, so the speed must drop to keep a star in a stable orbit. This is not just a theory. It is the fundamental orbital mechanics that governs everything from a satellite circling Earth to the Moon orbiting our planet. But when astronomers like Vera Rubin began to meticulously measure these stellar velocities, the data told a completely different and utterly baffling story. The rotation curves were not falling, they were flat. Stars far out in the galactic boondocks, in the sparse and dark outer regions, were hurtling around at the same tremendous speeds as those near the brilliant center. It was as if every car on a vast, sprawling highway, from the crowded downtown interchange to the most distant, empty stretch of road, was traveling at exactly 100 miles per hour. This was impossible. The galaxy, as it appeared to us, did not contain nearly enough mass to hold these speeding outer stars in their orbits. At those velocities, the centrifugal force should have flung them out into the blackness of intergalactic space, tearing the galaxy apart. The only logical conclusion was that our eyes were deceiving us. The visible galaxy of stars and gas was just the brightest part of a much larger, much more massive structure. It had to be surrounded by an immense, invisible halo of something that was providing the extra gravitational grip. This something did not shine. It did not absorb or emit light. It simply had mass, and it exerted a gravitational pull. The flat rotation curve was its signature, a ghostly hand holding the galaxy together. This phenomenon is not some rare cosmic fluke. We see it in majestic spiral galaxies, in football-shaped ellipticals, and in tiny, faint dwarf galaxies. Wherever we can measure the motion of stars or gas clouds, we find the same gravitational discrepancy. The phantom force is everywhere, a silent, invisible presence that has shaped every galaxy we have ever studied. The rotation curve is perhaps the most direct and intuitive evidence we have that we are missing most of the universe. It is not an abstract calculation from the early universe or a subtle distortion of distant light. It is a measurement of things moving in ways they should not, right here in our cosmic neighborhood, telling us that the universe is far more than what meets the eye. The smallest galaxies hold the biggest secrets. Dwarf galaxies are the faint, ghostly satellites that orbit larger galaxies like our own Milky Way. They contain only a few billion stars, a tiny fraction of the hundreds of billions in a major galaxy, and they emit a dim, diffuse light that makes them incredibly difficult to spot. But their faint appearance is a cosmic disguise, for within these unassuming structures lies the most concentrated evidence for the missing universe. In many dwarf galaxies, dark matter does not just dominate, it completely overwhelms. The ratio is staggering. In some of these tiny systems, over 99% of their total mass is this invisible substance. All the stars, all the gas, all the visible material you could ever hope to see amounts to less than 1% of what is actually there. This means these galaxies are not just held together by dark matter. They are, for all intents and purposes, dark matter itself, with a mere sprinkling of stars on top. This incredible imbalance makes them perfect natural laboratories. In a large, complex spiral galaxy, the physics of normal matter, what scientists call baryonic physics, creates a lot of noise. Supernova explosions, stellar winds, and magnetic fields all churn and reshape the visible components, complicating our view of the underlying dark matter. But in a simple, quiet dwarf galaxy, these complicating factors are minimal. The frantic dance of normal matter is reduced to a whisper, allowing the pure gravitational signature of dark matter to ring out with unmistakable clarity. This is why astronomers measure an extremely high mass-to-light ratio in these systems. It is a direct measure of how much mass you have for every unit of light you see. For the Sun, this ratio is 1:1. For a large galaxy like the Milky Way, it might be 10:1, meaning there is 10 times more mass than the light suggests. But for a dwarf galaxy, this ratio can skyrocket to 1,000:1 or even more. The numbers are so extreme they defy any conventional explanation. The phantom force is not just present, it is the entire show. Some of these dwarfs exhibit truly bizarre behavior, with stars moving in strange, unexpected patterns that suggest the dark matter halo within them is not a simple, smooth sphere. It might be lumpy or have a complex structure that gravity alone cannot explain. These tiny, faint galaxies are our clearest window into the invisible 95% of the cosmos. By studying the simplest systems, we hope to finally understand the complex force that built everything. But the phantom forces are not confined to holding single galaxies together. Their influence stretches across millions of light years, pulling on entire families of galaxies. Our own Milky Way is not drifting aimlessly through the void. It is caught in a vast cosmic river, flowing with thousands of other galaxies toward a single, mysterious point in space. This destination is known as the Great Attractor, and its gravitational pull is so immense it dictates the motion of our entire galactic neighborhood. It is the ultimate expression of the missing universe's power, a force so strong it can move superclusters of galaxies like leaves on a stream. Yet, for decades, its true nature remained one of the sky's greatest secrets, simply because we could not see it. This colossal gravitational heart lies in the direction of the constellations Centaurus and Hydra, but it is positioned directly behind the plane of our own galaxy. This region is called the Zone of Avoidance, a dusty, star-choked band of the Milky Way that obscures nearly 20% of the extragalactic sky. It is like trying to see a distant city while standing in the middle of a blinding fog bank. Our view of the Great Attractor is completely blocked by the gas, dust, and stars of our own galactic backyard. For a long time, this was a profound frustration. We could feel the pull, measure the undeniable current carrying us along, but we could not identify the source. What could possibly possess enough gravity to tug on so many galaxies? The answer, uncovered by piercing through the obscuring dust with infrared and radio telescopes, was both humbling and awe-inspiring. The Great Attractor is not a single monstrous object. It is the core of the Laniakea supercluster, our home supercluster, a vast web of galaxies 100,000 times more massive than the Milky Way. It is a gravitational focal point where the density of both visible galaxies and their attendant dark matter halos is at its absolute peak. This immense concentration of mass, most of it invisible, creates a gravitational well so deep that it bends the paths of galaxies for hundreds of millions of light years around it. We are not being pulled toward a void. We are being drawn into the heart of the largest structure we have ever belonged to, a metropolis of galaxies built upon a foundation of dark matter. The Great Attractor is the ultimate proof that the phantom forces shape not just galaxies, but the entire architecture and motion of the universe on its very largest scales. This hidden architecture, the dark matter halo, is the true form of a galaxy. What we see through our telescopes, the brilliant spiral arms and glowing core, is merely the brightest part of a structure that is overwhelmingly, invisibly vast. These halos are not small. They extend hundreds of thousands of light-years beyond the last visible star, a gargantuan sphere of invisible mass that holds the entire galactic system in its gravitational embrace. Without this unseen scaffolding, galaxies as we know them could never have formed in the first place. In the early universe, it was the gravity of these dark matter halos that acted first, drawing in wisps of ordinary hydrogen gas. Only once this gaseous material was collected and concentrated within the halo could it cool, condense, and eventually ignite into the first stars, seeding the brilliant galaxy at its heart. The halo is the potter, and the visible galaxy is the clay it shapes. But this influence is not a simple, uniform pull. The density of the dark matter halo changes dramatically from its core to its outer edges. It is at its most dense in the very center, creating a powerful gravitational anchor, and then it thins out gradually like a vast, ethereal atmosphere. This specific density profile is precisely what creates the flat rotation curves we observe. It explains why a star far out in the sparse outskirts feels a stronger gravitational tug than expected, because it is still submerged deep within the extended influence of this immense, invisible body. We can even map the subtle contours of these halos. One method uses the tiny, distorted images of background galaxies, their light bent by the halo's gravity. This gravitational lensing paints a precise picture of the halo's mass distribution. Another way is to study satellite dwarf galaxies. These tiny galaxies orbit the main galaxy like moons around a planet, and their paths are dictated entirely by the gravity of the dark matter halo. By tracking their movements, we are essentially tracing the invisible gravitational field lines of the halo itself. These observations reveal that halos are not perfect spheres. They are often slightly flattened or triaxial, like a cosmic melon, and their precise shape can dictate how the visible galaxy within them evolves, how its gas collapses to form stars, and even how it will interact with its galactic neighbors. Every galaxy we see is just the visible nucleus of a far greater, unseen entity. We are living in the bright, bustling downtown of a metropolis whose true suburbs are made of shadow, a hidden framework that has, from the beginning, held the blueprint for everything. Yet this visible sliver of the cosmos, this ordinary matter, is far from simple. It is everything we are made of, every star we see, every planet we have ever visited. Scientists call it baryonic matter, the term for all things built from protons, neutrons, and electrons. It is the stuff of galaxies and nebulae, of Earth and everyone on it. But for all its brilliance and complexity, it accounts for a shockingly small portion of the universe. All the stars in all the galaxies, every speck of cosmic dust, every wandering planet adds up to a mere 5% of the total mass and energy in existence. This is our reality. We are the rare exception in a cosmos dominated by the invisible, but the plot thickens because we cannot even find all of this 5%. A portion of the universe's ordinary matter has been missing for decades, playing a cosmic game of hide and seek. The leading suspect is a tenuous, superheated web of gas known as the warm-hot intergalactic medium, or WIMP. This is not gas gathered into neat galaxies. It is a sparse, incredibly hot fog strung along the invisible filaments of the cosmic web, the dark matter scaffolding we discussed earlier. Because it is so diffuse and so hot, it does not emit much light we can easily detect. It is the ghost of ordinary matter, and finding it is critical to balancing the cosmic books. This is where the phantom forces become our guide. We know dark matter's gravity shapes this vast, invisible architecture. The WIMP, being ordinary matter, is pulled by that same gravity, and it collects in these dark matter tendrils. So to find the missing ordinary matter, we must first understand the dark matter map. The visible universe and the invisible one are in a constant, intimate dance. The bright galaxies we study are not just passive ornaments, they are tracers responding to the gravitational tides of the unseen mass. By watching how galaxies move and cluster, we are essentially charting the contours of the dark matter landscape they are embedded within. This tiny, luminous fraction is our only window into the overwhelming dark. It is our sole clue in the greatest detective story ever told, a story where most of the characters are permanently hidden from view, their presence known only by the subtle motions they impose on the world of light. So even the familiar universe is playing a game of hide and seek. We just established that everything we are made of, all the stars and planets, is a tiny 5% of the cosmos. But here is the truly baffling part. When astronomers add up all that luminous matter, the grand total falls short. A significant chunk of that 5% is simply missing. After the Big Bang, the universe forged a specific amount of ordinary matter, the stuff we call baryons. We know this number with remarkable precision from the cosmic microwave background, that ancient echo from the dawn of time. It gives us a cosmic inventory, a precise count of how many protons and neutrons should be out there. But when we look around the modern universe, counting every star, every galaxy, every wisp of dust we can possibly detect, we come up short. We are missing a staggering 30 to 40% of all the ordinary matter that should exist. This is the missing baryon problem, a quiet mystery that has perplexed scientists for decades. If this matter is not gathered into bright, shining objects, then where in the universe could it possibly be hiding? The leading suspect is a ghostly, superheated fog known as the warm-hot intergalactic medium, or the WIMP. This is not a collection of galaxies. It is a sparse web of incredibly hot gas strung along the invisible filaments of the cosmic web, the dark matter scaffolding that forms the universe's large-scale structure. This gas is so tenuous and so energetic that it is a nightmare to observe. It is too hot to show up clearly in the light of optical telescopes, and in many cases, it is too cool to glow brightly in the X-ray spectrum our satellites are designed to detect. It is the ultimate cosmic camouflage, a haze of matter that has remained almost perfectly invisible. To find it, astronomers have had to become detectives, using the universe itself as a tool. One ingenious new method uses fast radio bursts. These are incredibly brief, ultra-energetic flashes of radio waves that come from deep space. As these bursts travel across the universe on their way to our telescopes, they pass through this intergalactic medium. The WIMP sparse gas leaves a tiny, telltale fingerprint on the radio signal, a specific dispersion that scientists can decode to map the location and density of this missing matter. It is like using a brilliant, distant lighthouse to see the faint outline of fog in a previously empty harbor. This search is separate from the hunt for dark matter, but it is no less profound. It reminds us that the universe's mysteries are not confined to the completely unknown. Even the part we thought we understood, the ordinary atoms that build our world, is still capable of surprising us, of hiding in plain sight and challenging our most careful observations. It is a humbling lesson that there is always more to discover, even in the light. But what if the entire premise is wrong? The search for dark matter is built on one core assumption, that our understanding of gravity, the force that shapes the cosmos, is complete. But a small, dedicated group of physicists proposes a far more radical alternative. They suggest there is no missing matter at all. Instead, the phantom forces we observe are the first clues that our grasp of gravity itself is flawed. The most famous of these ideas is called modified Newtonian dynamics, or MOND. It proposes a tiny but profound tweak to the laws of motion. At extremely low accelerations, like those experienced by a star on the lonely outskirts of a galaxy, the force of gravity would become slightly stronger than Isaac Newton or Albert Einstein predicted. This small change, this extra gravitational kick at the edges, could in theory explain why those outer stars orbit so quickly. They are not being held by an invisible hand of dark matter. They are simply responding to a different set of rules, a new law of gravity that only reveals itself in the deepest quiet of intergalactic space. For certain galaxies, MOND predictions are astonishingly accurate, matching the observed rotation curves with an elegance that dark matter models sometimes struggle to achieve. It is a beautifully simple solution that does away with the need to invent an entirely new, undetectable form of matter that has eluded capture for decades. Yet, for all its appeal, this alternative faces its own monumental challenges. The most famous evidence comes from a cosmic collision like the bullet cluster, where the source of gravity clearly separates from the visible matter, something a pure modification of gravity's laws cannot easily explain. The patterns in the cosmic microwave background, that ancient echo from the Big Bang, also require the presence of dark matter to form the universe we see. MOND in its basic form falls short. This has led to even more exotic theories like emergent gravity, which suggests gravity is not a fundamental force but a side effect of the universe's quantum information, or tensor vector scalar gravity, which adds new fields to Einstein's equations. These ideas are not mainstream. They are the bold, daring frontiers of physics, challenging the very foundations of general relativity, but their value is immense. They represent a crucial form of scientific skepticism, a necessary pressure test that ensures the dark matter paradigm is not accepted simply because it is the only idea on the table. They force us to question our deepest assumptions and ensure that every possible path, no matter how radical, is explored in our quest to understand the phantom forces weaving the cosmos together. The bullet cluster collision offers a stunning glimpse into the nature of the invisible universe. Here, two immense galaxy clusters have slammed into each other in one of the most energetic events since the Big Bang. This cosmic car crash separates the components of the universe with perfect, violent clarity. The clouds of superheated gas, which are made of normal, baryonic matter, behave exactly as you would expect. They slam into each other, creating a tremendous shockwave that glows brilliantly in X-ray light, and they slow down dramatically from the collision. This is the smoke of the impact, but when astronomers map the true source of gravity using gravitational lensing, they find something astonishing. The majority of the mass, the stuff that actually creates the gravitational pull, did not slow down at all. It has sailed completely through the collision, completely unaffected by the carnage, leaving the visible gas behind. This creates a clear and undeniable separation. The X-ray glow, which is the normal matter, is in one place. The gravitational mass, which is the dark matter, is in another. This is the closest thing we have to a smoking gun for dark matter. It demonstrates that the source of gravity is not tied to the stars or the gas. It is a separate, collisionless substance that interacts only through gravity, just as the theory predicts. For many scientists, this observation is nearly irrefutable proof that dark matter is a real, physical entity. Yet the debate is not entirely settled. Proponents of modified gravity theories have proposed their own complex interpretations, suggesting that the unique conditions of such a violent event could somehow mimic the effects of separated mass. These explanations are not the mainstream view, and they often require adding new assumptions, but their existence is a vital part of the scientific process. It ensures that every angle is explored. The bullet cluster stands as a critical test case, a natural laboratory where the universe itself performs an experiment for us. It showcases the incredible power of multi-wavelength astronomy, of using different eyes on the sky to see the same event in light, X-rays, and gravity itself. This single, spectacular collision provides some of the most direct evidence that we are indeed surrounded by a hidden reality, its presence revealed only when the visible universe is thrown into chaos. This technological revolution is already underway, with new eyes on the sky designed to see the invisible. The James Webb Space Telescope, peering deeper into the infrared than ever before, is not just looking at the first galaxies. It is studying their birth, tracing how the very first stars ignited within the gravitational wells of primordial dark matter halos. By observing the universe in its infancy, Webb helps us understand how the invisible scaffolding dictated the formation of everything we see today. Meanwhile, the European Space Agency's Euclid mission is undertaking a monumental cartographic project. It is creating the largest and most precise 3D map of the universe ever made, charting the positions and shapes of billions of galaxies. Its primary tool is weak gravitational lensing, measuring those tiny, telltale distortions in the shapes of distant galaxies to trace the distribution of the dark matter that warps the space between us and them. This map will reveal the cosmic web in stunning detail, showing the hidden architecture of dark matter on a scale never before possible. On the ground, the Vera Sea. Rubin Observatory in Chile will join this effort with its legacy survey of space and time. Every few nights for a decade, its enormous mirror and giant digital camera will capture an entire hemisphere of the sky, creating an unprecedented movie of the cosmos. It will detect billions of faint galaxies and measure the subtle gravitational lensing effects caused by dark matter, providing a vast statistical catalogue of its phantom presence. These observatories represent a new generation of discovery machines. They are not just looking for dark matter, they are mapping its influence with such precision that we might finally infer its true nature. The data they return could confirm our current theories, forcing specific dark matter particles into the light, or it could reveal something entirely unexpected, a flaw in our understanding so profound that it rewrites the laws of physics. We are on the verge of a great unveiling where the phantom forces may finally be forced to show themselves. Perhaps the answer lies not in our universe at all, but outside of it. When conventional explanations reach their limit, physics must venture into the profoundly speculative, into realms that sound more like science fiction than science. Some theorists propose that the phantom forces we observe are not from a missing substance within our cosmos, but are a gravitational echo from a reality beyond our own. The elegant but unproven framework of string theory suggests our universe may have more than the three spatial dimensions we experience. In this view, the force of gravity could be fundamentally different. It might be the only force capable of leaking or dissipating into these compact, hidden dimensions. From our perspective, this leakage would make gravity appear weaker on the largest scales, exactly mimicking the effects of an invisible mass pulling on galaxies. We would not be missing matter, but rather experiencing a diluted form of gravity. An even more radical idea posits that our universe is just one bubble in a vast multiverse, a frothing sea of cosmic foam where each bubble has its own unique physical laws. The gravitational pull we attribute to dark matter could be the subtle pressure from a neighboring universe residing mere millimeters away in a higher dimension, entirely invisible yet exerting a real force on our own. These concepts are the farthest frontiers of theoretical physics, untested and perhaps untestable with our current technology, but they serve a vital purpose. They demonstrate the breathtaking lengths to which science will go to solve a profound mystery, expanding the search from what is missing to where it might be hiding. This is not a surrender to the unknown, but an invitation to imagine realities so strange they redefine our very place in the cosmos. This realization forces a profound shift in our entire worldview. For centuries, we have trusted our senses to reveal the nature of reality, believing that what we see is what exists. Now, we must confront the unsettling truth that the universe presented to our eyes is a mere facade, a glittering decoration draped over a hidden framework of immense, invisible power. This is not just a scientific adjustment. It is a philosophical earthquake that shakes the very foundations of how we understand our place in the cosmos. We are forced into a new kind of humility, one far deeper than the Copernican revolution that merely moved us from the center of the universe. That discovery told us we were not in a privileged location. This new discovery tells us we are not even made of the primary stuff of reality. We and everything we have ever known or touched are the exception, a rare and luminous afterthought in a cosmos dominated by shadow. It begs a fundamental question about the nature of existence itself. If dark matter does not interact with light, if it cannot be seen, touched, or directly measured with any instrument we possess, in what sense can we say it is real? Our traditional definition of reality is tied inextricably to interaction. We know something exists because we can poke it, see it, or detect its influence on other things we can see. Dark matter challenges that definition to its core, forcing us to accept that reality might be far vaster and more strange than our human-centered definitions can contain. This search for the missing universe, then, is more than a technical puzzle for physicists. It is the latest chapter in humanity's eternal quest to understand the true nature of existence, a journey that connects the most advanced quantum detectors to the most ancient philosophical questions about what is real and what is mere illusion. Despite the overwhelming evidence, dark matter is often shrouded in public confusion and wild speculation. It is not a supernatural force or a void of nothingness, and it is absolutely not the same as dark energy, its cosmic counterpart that pushes the universe apart. These are distinct phenomena with unique roles in the cosmos, both backed by decades of rigorous observation and measurement. Another frequent mistake is the idea that dark matter could be made of known objects like black holes or rogue planets. While that was an early consideration, detailed surveys have ruled this out. There simply are not enough of these objects to account for the immense gravitational effects we see across the entire universe. The leading hypothesis remains far more fundamental, pointing to an entirely new type of elementary particle that simply does not interact with light. This distinction is crucial. It moves the conversation from science fiction into the realm of hard science, where hypotheses are tested, refined, and sometimes discarded based on cold, hard data. Understanding this rigor transforms the mystery from a vague wonder into a tangible puzzle that the scientific method is uniquely equipped to solve. By clearing away these misconceptions, we do more than just correct facts. We open a door to the truly awe-inspiring nature of the hunt, showing that the greatest adventures in human history are not about chasing myths, but about patiently unraveling the real and profound secrets of our universe. This clarity is what will inspire the curious minds who will one day solve this mystery for us all. This cosmic puzzle is not just a challenge for professional scientists in their labs. It is a story that belongs to all of us, a mystery so profound it has the power to ignite a passion for discovery in anyone who hears it. Planetariums around the world use the enigma of dark matter to captivate audiences, their domes becoming portals to the invisible universe. Museums build interactive exhibits where you can literally feel the pull of gravity and see simulations of how dark matter shapes the cosmos. These are not just displays. They are invitations to think differently, to question what is real, and to understand the scientific process of observation, hypothesis, and testing. Online, vast digital libraries and video courses break down complex physics into engaging, digestible stories, making this cutting-edge knowledge accessible to a global audience. The goal is to build a foundation of scientific literacy, empowering people to separate fact from fiction in a world flooded with information. This educational outreach transforms the public from passive observers into active participants in the greatest detective story of all time. By making the mystery accessible, we are building a world that values curiosity, evidence, and the relentless pursuit of truth. No single field of science can solve this cosmic puzzle alone. The search for the phantom forces is a symphony of disciplines, each playing a crucial part in the grand orchestra of discovery. Particle physicists design exquisitely sensitive detectors to catch the uncatchable, while astronomers act as the lookouts, scanning the skies for the gravitational footprints of the unseen. Cosmologists are the master architects, building theoretical models of the entire universe to see which blueprint fits the data. Even philosophers join the conversation, helping us grapple with what it means for our reality to be built upon a foundation we cannot perceive. This collaboration extends to the digital realm, where computer scientists run vast cosmic simulations on some of the world's most powerful supercomputers, creating entire virtual universes to test our ideas. And none of this would be possible without the engineers, the practical wizards who turn abstract concepts into tangible reality, building telescopes that orbit the Earth and instruments that see in wavelengths of light invisible to our eyes. This fusion of skills is our greatest strength. An astronomer's puzzling observation can send a particle physicist back to the drawing board. A cosmologist's new model can tell an engineer what to look for in the next generation of telescopes. It transforms a solitary search into a collective human endeavor, a shared project to understand our place in a cosmos that is overwhelmingly strange. The greatest mysteries refuse to be confined to a single textbook. They spill over the artificial boundaries we create, demanding that we bring every tool we have and every mind we can to the table. The relentless pursuit of the invisible has a remarkable way of illuminating our own world with tangible, life-changing benefits, while we build ever more sensitive detectors to catch a ghostly particle. The technology we create in the process often finds a second life here on Earth. The ultra-pure liquid xenon chambers designed to sense a single dark matter collision are now being adapted for revolutionary new medical imaging devices, offering doctors a clearer window into the human body. The advanced radiation monitoring systems that guard these experiments from background noise are improving safety protocols in nuclear power plants and hospitals. This technological cross-pollination is a constant, quiet miracle of fundamental research. The ambitious space missions we launch to map the cosmic web demand incredible advances in satellite stability, precision optics, and data transmission, all of which trickle down to improve the satellites we use for weather forecasting, global communication, and navigation. Even the complex algorithms written to simulate the birth of a universe are now used by financial institutions to model market risks and by shipping companies to optimize global logistics networks, saving immense amounts of time, fuel, and money. This demonstrates a powerful truth about curiosity-driven science. The quest to answer a profound cosmic question does not exist in an ivory tower. It acts as a powerful engine for innovation, spinning off new technologies, creating high-tech jobs, and driving economic growth in ways that are often impossible to predict at the outset. But the payoff is not merely economic or technological. This grand endeavor feeds our collective imagination, inspiring new generations of scientists, engineers, and artists. It reminds us that we are part of a vast, mysterious, and beautiful cosmos, a realization that enriches our culture and deepens our understanding of our own place within it. The search for the missing universe, therefore, is far more than an astronomical specialty. It is a deeply human project that pays dividends across society, proving that when we reach for the stars, we inevitably improve life on the ground. Every great leap in human understanding arrives with a profound responsibility. The search for the phantom forces of the universe is no different, for this is not just a scientific quest but a deeply human one with real-world consequences. The staggering energy potential locked within even a single dark matter particle, if it could ever be isolated and manipulated, presents both an incredible promise and a sobering peril. Could it become an inexhaustible, clean power source, lifting humanity into a new era? Or could its unimaginable density be twisted into a weapon of terrifying scale? This is not science fiction. It is the essential ethical foresight that must accompany our curiosity, ensuring that a discovery meant to unveil the cosmos does not instead become a tool for its destruction. The very act of looking so far outward forces us to look inward, to question our own readiness to steward such fundamental power. It compels us to build frameworks for international collaboration and transparent oversight long before a discovery is made, creating a global conversation about how such knowledge should be used for the benefit of all humanity and not for the advantage of a few. This responsibility extends beyond the laboratory walls to the very resources required for the search. The immense funding for particle colliders and space telescopes inevitably raises a vital question. In a world grappling with immediate crises like poverty, disease, and climate change, can we justify spending billions to hunt for an invisible particle? This is not a question with a simple answer, but a necessary tension that scientists and society must navigate together. The pursuit of fundamental knowledge is not a luxury disconnected from our earthly problems. It is the foundation upon which our future solutions are built. The very technologies developed to peer into the cosmos consistently spin off into medical imaging, global communications, and environmental monitoring, addressing those very earthly needs. The quest to understand our universe is a long-term investment in human potential, a declaration that our aspirations can be as vast as the cosmos itself, while never forgetting our duty to the world we call home. Scientific history is filled with moments of brilliant accident. Some of our greatest discoveries arrived not through meticulous planning, but through a fortunate stumble, a curious anomaly that a prepared mind refused to ignore. The story of the cosmic microwave background is a perfect example. It was found not by astronomers seeking the Big Bang's echo, but by two radio engineers, Arno Penzias and Robert Wilson, who were deeply frustrated by an persistent, inexplicable hiss in their giant horn antenna. They scrubbed away pigeon droppings and checked every connection, but the noise remained. That stubborn, universal static, which they initially saw as a nuisance, was in fact the cooled remnant of the universe's fiery birth, the most important fossil in all of cosmology. They were listening to the creation of everything, and they almost tuned it out. This pattern repeats itself across science. Penicillin, X-rays, even the structure of benzene, all were discovered because someone noticed something odd and chose to investigate instead of dismiss. The hunt for the phantom forces is ripe for such a moment. We are building massive machines to find specific particles, but the universe might have a different surprise in store. The true answer might not be a WIMP or an action, but an entirely unknown particle with properties we have not yet dreamed of. Or perhaps we will find that dark matter is not a particle at all, but a manifestation of a fifth fundamental force that only operates on galactic scales. The key is to remain open, to cultivate a mindset that treasures the unexpected result as much as the confirmed hypothesis. This is the beautiful unpredictability of science. It is not a straight path to truth, but a winding road full of wrong turns that often lead to the most spectacular vistas. The greatest discovery in this search may not be the thing we are looking for, but the thing we never imagined. This global pursuit is a testament to our shared humanity, a collaborative effort that stretches across every continent. The search for the phantom forces is not owned by any single nation or institution. It is a collective human project, uniting scientists from countless countries in a shared mission to understand the cosmos. The tools of this search are themselves monuments to our ability to cooperate. The Large Hadron Collider in Europe is operated by scientists from over 100 countries. The James Webb Space Telescope is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. The upcoming Vera Rubin Observatory in Chile involves a global collaboration of dozens of universities and research institutes. These are not just scientific instruments. They are diplomatic achievements built on a foundation of shared funding, shared expertise, and a shared dream. In a world often fractured by political and cultural divides, these projects stand as powerful counterexamples. They prove that humanity can set aside its differences and work together on a breathtaking scale, driven by a common curiosity that transcends borders. This scientific collaboration does more than just advance knowledge. It builds lasting bridges between cultures, fostering friendships and mutual respect among researchers who might otherwise never meet. It creates a global network of minds, all focused on the same profound mystery, demonstrating that our greatest challenges are best faced not in isolation, but together. This unifying power of science offers a hopeful vision, one where the desire to understand the universe becomes a force that brings us all closer. Our journey through the phantom forces of the cosmos brings us to a profound and humbling truth. We have traced the evidence from the stubborn intuition of Fritz Zwicky to the meticulous measurements of Vera Rubin, from the ghostly fingerprints in spinning galaxies to the cosmic wreckage of the bullet cluster. We have built detectors deep underground and launched telescopes into the void, all in pursuit of an answer to a single, staggering question. What is the true nature of the universe when most of it remains hidden from our view? Whether the answer lies in an exotic particle, a rewrite of gravity's laws, or a reality beyond our own dimensions, this search represents one of the most thrilling chapters in the entire story of science. It is a powerful reminder that our understanding of the cosmos is not a finished book but a living, breathing narrative, constantly being revised and expanded with each new discovery. The greatest mysteries are not obstacles to our knowledge but invitations to dive deeper, to question our assumptions, and to push the boundaries of what we believe is possible. As our technology grows ever more powerful, the answers we seek may be closer than we think, waiting just beyond the edge of our current perception. But even when we solve this puzzle, new and even more wonderful questions will undoubtedly emerge from the darkness. So the next time you find yourself beneath a starry sky, remember to look past the points of light. Consider the vast, invisible architecture that holds it all together, the silent, phantom forces weaving the grand tapestry of existence. I would love to hear what you think about this cosmic mystery. Share your thoughts and questions in the comments below. Subscribe for more journeys to the edge of understanding, and join us as we continue to explore the universe's greatest secrets.